Hi, this is Mrs. LaBarbera. This is AP Physics Mechanics C. Today I want to talk about an object hanging on the spring. So a spring of negligible mass and with a spring constant 50 Newton per meter is hung vertically, as shown in the figure on the left. A block of mass 1 kilogram is attached to the spring and slowly lowered at a distance x0 until it comes at rest at equilibrium position as shown in the figure on the right. Part A, on the dot below that represents the block, draw and label the forces, not the components that act on the block when it is at equilibrium position as shown. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So when it's at equilibrium position, there are just two forces. One is gravity, the other is force of spring. At equilibrium, these two forces should be the same. Part B, calculate the distance x0 that the spring is stretched from its original length to the equilibrium position. Here is x0. So we know these two forces has to be the same. Fs, according to Hooke's law, that's kx0. That should be equal to mg. We know m, we know g, we know k. Simply substitute your number. You should have x0 equals to 0.2 meter. Well, the 1 kilogram block is in equilibrium. A 0.2 kilogram ball of clay is launched with speed v0, vertically up from the ground, 1 meters below the hanging block. The clay has a speed v1 equals to 5 meters per second when it collides with the block. So right before it touches the block, its speed is 5 meters per second. Calculate speed v0. So this is kinematic question. We know the final speed, we know the distance, we know acceleration. This is free fall in this part, and we have to find the initial velocity. So from here, we can use the kinematic equation. We can find initial velocity, substitute the numbers. Your initial velocity should be 6.68 meters per second. Upon impact, the clay stick to the 1 kilogram block. D, part 1, calculate the speed of the block immediately after collision. This is a collision, so we know momentum should be conserved. P before equals to P after. What we know, m1, that's the clay. Speed 1 right before collision, m2 is the block, and v2 it was at rest. The two moved together. What's v prime equals to? That's the momentum conservation equation. Simply plug in your numbers, you should have v prime. I cancel this out because v2 equals to 0. And v prime equals to 0.83 meters per second. D, part 2, calculate kinetic energy lost in the collision. So kinetic energy lost, not necessarily to be a negative number. It's just a number, like it could be less than before, but what is the actual number doesn't have to be a negative. So it's really is the absolute value between the difference. We know k equals to 1/2 mv squared. Plug in the number to find k2 and k1. K1 initially, the clay has 5 meters per second and its mass is 0.2. So clay before the collision has 2.5 joules. After the two stick together, so you have to add the mass and the two moving at 0.83 meters per second squared. So here is after how much energy is lost is the difference between these two. That's 2.1 joule. D, part 3, determine the period of oscillation for the block clay spring system. So the period for oscillating system is equals to 2 pi square root of m over k. This is in oscillation, the simple harmonic motion equation. So we know m, to the block and the spring stick together. We know what k is. Simply substitute your numbers, and you have you have t should be 0.97 seconds. Part E, when an oscillating block clay spring system reaches its maximum speed after collision, will the spring be stretched from its original length by a distance greater than, less than, or equal to x0? Justify your answer. So let's see what happens. When does it reach maximum speed? Maximum speed happens at equilibrium position when the acceleration changes direction, right? Since the block clay system has more mass, so the spring will stretch more than x naught at equilibrium position. Take a look at this picture. So this is just a block, how much is stretched. Now if you have the clay, here you're going to have more mass, so you're going to stretch a lot more. I just want to emphasize again, the maximum speed happens at equilibrium position. This is why before it reaches equilibrium position, the net force is downward. So the block is going to speed up. At equilibrium position, net force equals to 0, acceleration equal to 0. When you stretch past equilibrium position, the net force is upward, so acceleration is up, but velocity is down. That's why the block is going to slow down. That's why at equilibrium, it has maximum speed. Part F. The collision is repeated using a rubber ball with the same mass as the ball of clay. The rubber ball is launched vertically with the same speed v0. The collision between the rubber ball and the block is elastic. Will the speed of the block immediately after colliding with the rubber ball be greater than, less than, or equal to the speed of the block? You calculate it in D1. Remember, D1 is the clay and the block sticking together. So justify your answer. So in this case, what does elastic mean? Collision. Elastic collision means the ball has to bounce back, right? If the two stick together, this is conservation momentum. We know initially the block is 0, so we can solve the block's speed as this. This is block and the clay's speed. If you are bouncing, here is the new conservation momentum. These two are separating. So again, the second term is 0, so you can solve for v2 prime. This is the speed of the block after collision equals m1v1 minus m1v1 prime divided by m2. But because the collision is elastic, so v1 prime is going to be negative. When you subtract the negative number, you add it. So that the top is going to be bigger, but the denominator is smaller. So mathematically, v2 prime will have a bigger value than v prime, right? Since the collision is elastic, the rubber ball is bouncing back. v1 prime is negative, so v2 prime is going to have a bigger value. That means the block will have a greater speed after colliding with the rubber ball. Another way to think about this is this. Since the collision is elastic, kinetic energy is conserved. If kinetic energy is conserved, the block will have a greater speed after colliding with the rubber ball. That's it for today. Thanks for watching. See you next time.